Thank you for inviting me to give this talk. I'll be talking about SLIC spectroscopy of common organic molecules at 6.5 millitesla. And this is a project funded by an STTR from NSF with my company, for full disclosure here, Scalar Magnetics, and in coordination with Matt at Martino Center. So John Blanchard helped me out here by giving a lot of good reasons about why it's nice to sometimes work at low fields. And if you look at the plot on the left, you can see over the years, the NMR field has been going up and up, and we're moving in the opposite direction into kind of prehistory here. However, there's benefits. For example, it's cheaper and easier to create these fields. So from Stefan's talk this morning, you saw, it's easy to make an electromagnetic system. And these can be scalable even to very small size, perhaps down to lab on a chip size. Certain detection methods also work better at low fields. So the rubidium vapor cells and also nitrogen vacancies in diamond for nanoscale spectroscopy, for instance. Unfortunately, classical homonuclear NMR spectroscopy fails at low fields, particularly under the conditions when the J coupling becomes greater than your chemical shift differences, your spectral dispersion. In that case, the spins become nearly equivalent, and you end up getting just a single spectral line. So, for example, ethanol here at 4.7 T shows a beautiful pattern you can use to identify ethanol. But if we go down to 6.5 milliteslas, in Matt's magnet, you just get a single spectral line. Now, there are some methods for doing low field NMR, as John mentioned before. And here's a nice spectrum of ethanol from his thesis. You can measure it via this low field Zolf J coupling spectroscopy. However, in that case, you require a heteronucleus to break the near equivalence and make it work. So it's limited to molecules with a spin half heteronucleus, or you'll be using natural abundance, C13, which is only 1%. So you're already 100-fold, taking a 100-fold hit in your signal if you do that. You can also do relaxometry. So you can measure T1 and T2 to try to distinguish species, also using diffusivity, for instance. So in this case, they separated water from oil based on those two aspects. But this doesn't give you a whole lot of information for actually identifying the chemical. So we're working on another approach, which we call SLIC spectroscopy. And to understand this, we can first look at just a two-spin system with J coupling. Let's say we had two spins at a low field. And you would get your single line, which is strong, but it's a degenerate Zeeman transition. So it's the transitions between your three singlet states. Singlet to triplet transitions are basically forbidden and very weak and scale as your chemical shift difference over J. So this can become very small and hard to detect. So what we do is a different form of NMR in the rotating frame. And we use this neat trick and phenomenon that basically energy levels in your rotating frame can be controlled by your spin locking. And the triplet states are split by the energy level of this spin lock pulse, so the nutation frequency. And as Professor Warren pointed out, this is essentially analogous to the AC Stark effect in electronic systems. So in a way, this is a form of Stark spectroscopy. Now, what happens is that when you get a level crossing between any of these states, in certain cases, you can get this anti-crossing. So there's an energy gap, and your magnetization can be transferred from one state to another, driven by any small chemical shift differences. When this happens, you can actually transfer magnetization into a dark state. For example, here, triplet to singlet, which then produces a dip in your FID magnetization. So here in the two-spin system, when J coupling equals the spin lock mutation frequency, you get this dip, and you can measure what J is. Now you can expand this to more complex systems. For example, ethanol, which we showed back in 2014 at 6.5 millitesla, and you get more complex J coupling spectra. In this case, we were able to show that there's a difference between anhydrous ethanol and hydrated ethanol based on whether the hydroxyl proton is coupling or not. And it was also demonstrated by Danila Barsky and co-workers in the parahydrogen polarized case of propane at 50 millitesla to show a nice spectrum with lines at multiples of J. In the meantime, we've greatly improved some aspects of Matt's system, and we've set out to study this on a larger variety of molecules to look at the limitations and the strength of this technique. So we're using Matt's 6.5 millitesla system. NMR frequency is 276 kilohertz. And we've done some improvements to lock B0 to within 0.25 hertz. Also use an active TR switch to preserve the shape of our SLIC pulses at these very low powers. And in fact, all of our pulses are so weak that we don't even need to use the power amplifier. We use a solenoidal coil for B1, and we're doing this mostly on neat or very concentrated samples. So we can look at some examples first of this, what I'll call the ethanol family, a methylene group and a methyl group coupled together. And if we analyze the energy levels, we see that there are crossings where magnetization transfer can occur at 3J/2 and 5J/2. And indeed, we see in all of these cases, ethyl acetate, hydrated ethanol, and 2-butanone dips at those locations. And from that, we can measure their J coupling. Now, some things to notice about this, ethyl acetate and butanone also have a methyl group here, but the J coupling is essentially 0 to the rest of the groups, so it doesn't show up in the spectrum. It just adds to the background. In this case, 70% ethanol, the water exchanges so quickly with its hydroxyl group that the net J coupling effectively is 0, and you can have the same effect. On the other hand, in anhydrous ethanol, where this proton stays attached for a very long time, you get a totally different spectrum. And that's because our energy states are now completely different, and you have an A3B2C system. So we can tell the difference between the two. Now notice that some of these lines are much broader than what we predicted in our simulation, and that's due to a couple of reasons. One is that in some of these cases, we spin lock for a time that's actually longer than the optimal transfer time, and we end up getting these wiggles in our spectrum here. We don't really have enough resolution and SNR to see those, so they're probably contributing to some broadening. Number two, if you have a short relaxation time of one of the two states that's crossing, so that the energy level is not as well defined, of course, you will get broadening as well. And thirdly, you could have B1 inhomogeneity. However, in that case, the broadening would actually vary with mutation frequency. From our Rabi calibration curves, we can show that our homogeneity is better than 1%. And you would only really see broadening when it reaches 3% or higher. So that's not really contributing to broadening in our spectrum. Continuing on, if we had another proton, so in this case, a methyl group and two methylene groups, for example, hydrated propanol or methoxypropane, it starts to again look similar to the anhydrous ethanol case. And the dips start moving to lower frequencies. Now, what's interesting about these two cases is that they're actually very sensitive to weak J couplings that you normally would require a high resolution spectrum to really see. So the coupling between A and C protons, the 4J proton-proton coupling, has a much larger effect than one might expect. If we model the spectrum for possibilities between minus 0.8 hertz and 0.8, you can see that there's a big shift, which is actually very easy to measure. And from matching simulations to our data, we found that it's around minus 0.2 hertz for propanol and around 0 for methoxypropane. The other thing that's nice is that it is different for the two different signs of the coupling, which would not be obvious just from a conventional NMR spectrum. Now, if we keep going and get to bigger and bigger spin systems, such as butanol, we see that we start to have a problem. And that is that, first of all, things get shifted to lower and lower frequencies, and we get broader and broader ugly spectrums. Now, why does this happen? Well, it's much like the electronic conjugated systems, or also icing chains, in that when you have too many coupled spins, you start to create a continuum with more of bands that create broad weak dips instead of very specific energy levels. These also tend to have shorter T1s, so we can't spin lock as long, and you get broader dips. There is a limitation to the technique. When symmetry is a little higher, for example, methyl isobutyl ketone here, it's a little better, but again, we don't really have the SNR in this case to see some of these smaller dips. We can see the same effect on rings. So in this case, going from a ring with 3 methylene groups to 4 and to 5, we see that our dips start to move to lower frequencies. And by the time we have 10 spins in pyridine, we get some really broad, ugly looking resonance. However, if instead of methylene groups, we have an aromatic system like pyridazine or pyridine, because there are fewer overlapping crossings, we still get very nice dips here. And we can distinguish them both by the frequency and the extra dip for pyridine. Another interesting point on these is that many of these have quadrupolar nitrogen-14, but it relaxes quickly and does not effectively couple to the protons, so there's no major effect from that. We also can show this for chloropropanes and chloropropanes. Now, the nice thing about these is that they have very long T1s, so we get very well-defined spectra, which are in good agreement with the theory. And we can easily distinguish between all these structural isomers, including between cis and trans, whose high field spectrum is not all that different from one another, but clearly at low field, here we can see a major difference because the J couplings are so different from one another. Again, even though chlorine is quadrupolar, the lifetimes are so short that it does not affect the spectrum. So in conclusion, we've showed that SLIC can measure unique spectra for many molecules at low field strength. We don't require heteronuclei, but we do need a small chemical shift difference. So something like water or acetone will just show up as a single line, and we're not going to get any dips in our SLIC spectrum from those. It's not affected by quickly relaxing quadrupolar nuclei. However, my guess would be something like deuterium may show up. It also, however, has the benefits of being sensitive to long-range coupling, as well as chemical exchange, which may be useful. It works best on groups of spins, roughly 10 or fewer, and with T1s greater than around half a second or longer. Now, this doesn't mean it can't work on large molecules. It just means that you need to have some groups that are somewhat isolated, as opposed to, a long alkane or something like that. And there are interesting aspects of relaxation which require further exploration and are somewhat interesting because in our case, we are looking at states that encompass all of the protons, in these groups, so across the whole molecule, which might tell us something interesting about molecular dynamics. So with that, thank you, and thanks to Matt, who's during the pandemic was working hard, making these samples and measuring things in his magnet and learning some chemical techniques. So thank you, and I'll take questions.
Awesome. Thank you, Stephen, for an amazing talk. It's so exciting to see, I think, these the chemical differentiation at low magnetic field is just incredible with the SLIC technique. I guess we have a few questions. First questions from John Blanchard is, what determines the line widths of?
Sure. So a couple things. One is how long you spin lock. So the first order, the shape of this line, it's just the Fourier transform of how long your spin lock is, right? So if you spin lock for 2 or 3 or 4 seconds, you get a very narrow line. But of course, then you have T1 row relaxation, which is going to limit your signal, as well as the relaxation of these 2 relaxing states. So again, if one of the states relaxes quickly and has a poorly defined energy, you're not going to get a very narrow line. And then B1 inhomogeneity, if you're not careful, will come into play at some point as well. So it's some convolution of those 3 effects mainly.
I guess I had another question as well, which is about, I guess, the baseline noise that you were seeing in these different spectra. So especially I was looking at like the pyridine or like the pyrazine, some of the aromatic systems versus like the dichloropropane. Exactly. The dichloropropane, the baseline was so clean, but in those aromatic systems, it was pretty noisy. What's the...
Right, a lot of that has to do with T1, which is essentially the same as T1 row at these fields. So, right, if you have nice long T1s, you don't lose as much signal, and we have better SNR, so that helps. These are all thermally polarized, so we naturally have somewhat small signals at 6.5 millitesla.